for those of you who don't know me, I'm Jay Kroll. I also go by Alec. That's how you'll find me on social media. I use masculine gender pronouns, he, his, and him. And I'm a graduate student at the University of Colorado, where I study, one, how gender and sexuality affect the academic outcomes for Gen Chem students. More topically, I also study sulfur reactions in planetary atmospheres. I'm not going to talk to you about either of those things this morning. I'm going to talk to you about, oh, come on. Rocks. Cool. So more specifically, I'm going to talk to you a little bit about some of the rocks that you're going to hear about in this morning's session and why we care about them as astrobiologists. To the geologists in the room, please forgive me and correct me during the session after. So the first rock that we're going to talk about is Venus. It's often referred to as Earth's twin. More accurately, it might be described as our evil twin on a bad hair day. But it's very similar to Earth in size and mass and composition. But a couple of things make it very notably different, especially at sulfuric acid clouds. So from about 50 to 70 kilometers, there's a global sulfuric acid cloud layer. It also has an incredibly slow day. So it takes about 243 Earth days for Venus to turn once on its axis, and it also rotates in the opposite direction of all of the other planets. This is likely because of some massive cataclysmic collision earlier in its history. It also is incredibly hot. At its surface, about 500 degrees Celsius. And if we take a look at its atmosphere, that's a little bit easier to explain. The surface pressure is 93 bar. It's almost 100 times more pressure at its surface than on Earth. And that atmosphere is almost entirely carbon dioxide. And so it has this incredibly potent greenhouse gas atmosphere. There's some nitrogen as well as some other trace gases, most notably SO2. But because of that global cloud cover, it has this incredibly high albedo, which means that almost 90% of the light that is incoming from the sun actually gets reflected away from Venus. But the atmosphere is so thick that even that 10% that gets in and absorbed by the planet leads to incredible heating of the surface. There's also very little hydrogen in Venus's atmosphere, and there's an incredibly high D to H ratio. And so what that tells us is that actually Venus has probably lost a lot of the water from it, which is interesting because early on in its history, we think Venus may have been a lot more like Earth and had oceans on its surface. Today, its surface looks incredibly different though. Because of its similar size and density, we assume that it's pretty similar to Earth and that it has a core, a mantle, and a crust. However, we don't have a lot of actual direct evidence about the internal structure of the planet. We don't see any evidence of plate tectonics, which is pretty interesting, and there's no magnetic field. However, most of the impact craters are almost in pristine condition. The surface is very young, only about 300 to 600 million years old. And there's been a lot of evidence of past volcanic activity. And so what we think happens on Venus is that the crust is, we don't have any of these plate tectonics right now, but the mantle slowly heats up, and at some point there's enough energy to actually disrupt the crust. And then we see massive turnover of the surface and resurfacing of the entire planet. So if we go a little bit farther out in our solar system, we've got Titan. It's the largest moon orbiting Saturn, but perhaps most interesting is that it's the only moon with a dense atmosphere. And the surface is composed mostly of water ice and rocky material. But this dense atmosphere is possibly an analog to early Earth's atmosphere, which is what makes it really interesting to us as astrobiologists. And so its atmosphere actually has a very similar structure to Earth. It has this troposphere where we see all of its weather, and then an upper stratosphere where there's this tholin haze, which is mostly carbon-containing organics with some nitrogen in them, and then a mesosphere and thermosphere. Its atmosphere is almost entirely nitrogen. It's about 98% nitrogen. We do see some methane. It's 1.2% overall, but as you go closer to the surface, it actually increases to about 5% of the atmosphere. And that's because it's incredibly cold, and so that methane actually begins to freeze out, and you get precipitation of it on the planet in this lower troposphere. There's a little bit of hydrogen, and then there's a lot of trace organics formed because of the photochemistry that goes on with methane. Before Cassini-Huygens, we actually did not know a whole lot about Titan's surface. Thanks to that mission, we actually do now know that there are hydrocarbon lakes and rivers, and that the surface is actually pretty geologically young, somewhere between 100 million and a billion years old. But we can actually see these canals and rivers on the surface, as well as a number of lakes at the northern pole of the moon as well. And then also particularly interesting, it has a rocky silicate core about 3,400 kilometers in diameter. So it's a little bit bigger than Earth's moon, but smaller than the Earth. But there's a lot of evidence that there is a subsurface ocean, possibly a global ocean. And what we think would allow for this is actually an ammonia-water mixture. So once you have enough ammonia in that water, you can get this eutectic mixture that doesn't freeze out until much colder. And so that also gives us the potential for a lot of interesting chemistry and importance for astrobiology. The next rock that we're probably going to hear about is meteoroids. And the IAU definition is incredibly specific. It's a solid object moving in the interplanetary space of size considerably smaller than an asteroid and considerably larger than an atom. And so this actually gives us a pretty wide berth, but most of these things are about 4.5 billion years old. And perhaps most interestingly, about 15,000 metric tons of these are delivered to Earth every year. And so these are a source of incoming material that can seed the planet with a lot of interesting material over the course of billions of years. Additionally, most of them come from the asteroid belt. About 99.8% of meteorites that we've found have come from there. And so they can tell us a lot about the early solar system composition. Some as well are cometary debris, and so that's normally what we would refer to as like a meteor shower. And then a very small number of them are ejected material from collisions with much larger bodies, such as Mars and the Moon. And so these are some of the first hints that we got at what the composition of Mars and the Moon were. After that, we'll hear about some stromatolites. And stromatolites are a little bit different than all the other rocks we'll be talking about. One, they're here on Earth, which is exciting, but they're built by living microbial colonies of cyanobacteria. And on the modern Earth, they're actually found in only a very few select places, such as Shark Bay and in the Caribbean. This is because they have to form in very hypersaline conditions, and I'll talk a little more about that here. In the Precambrian area, they were fairly ubiquitous all over the planet, and they may date back all the way back to the Archean. So they're some of the earliest forms of life that we see on the planet that we actually have like really nice records of. And so the way these things form, cyanobacteria are these photosynthetic species. So they need to be able to get sunlight to grow, but you get these mats of cyanobacteria, and then they form on these shallow waters. The deepest have been found about 14 meters or 45 feet. But as they do that, they build up this mucus layer that can trap sediment, or they can precipitate calcite as well. But as that happens, then they grow up through that layer, and they start a new mat. And then they grow out, and then they collect more sediment, and then they get another layer, and they grow up through it, and then they start another layer. And they do this over and over again. And so they trap a lot of the interesting material, so they tell us a lot about what the conditions were when they were growing, what was available, what was settling out in the oceans. But it's important that they need to be free of any sort of grazing species. So if anything eats them, then they can't build these rocks. That's very problematic in today's oceans. However, Precambrian. There weren't any fish or anything eating them, so we have a lot of them around. And you get them in all sorts of really interesting structures, from domes to columns to splitting columns. And then the last rock, we'll call it a rock, iron sulfur clusters. Think of them as very tiny rocks that are important in biology. But they're made out of, unsurprisingly, iron and sulfur. And they come in a really wide variety of different structures depending on how much iron and sulfur you have in them. Anywhere from very simple 1 and 2 atoms of iron and sulfur up to much larger structures. But interestingly, they're found in a number of proteins in biology, and there's at least 3 biosynthetic systems that have been identified for making these things in our biological systems. And what's really interesting is they play a really important role in redox oxidation reactions in mitochondria. So both complex 1 and 2 and oxidative phosphorylation have multiple iron-sulfur clusters in them. They can also act as catalytic centers for a lot of biological activity. And because of this, they've been suggested as playing an important role in the origin of life on Earth. And so with that, I will thank you guys for your time and hand things over to the experts that are going to be giving talks there. I call them the rock stars of this morning's session.